Right. We'll get started. We had a bit of time, and I updated the schedule for the remainder of the semester. So today we're going to do these lectures on patterns, memory, and visual encodings. On Wednesday, I'd like that we get back to the projects. So I'm going to ask that every group is going to present a status update with some type of risk assessment and an updated timeline, so that we know that we're in track. And then I'll try to present how you can run the presentation for the final project presentation, and also how you can work to set up the paper. So this means that we have, let's see, four people in class today. So Wednesday, I'm expecting that I have at least one representative for each one of the groups that is going to come and do the status update. I'd rather not enforce it, but if it comes to that, then I guess I'll need to enforce it. So make sure that somebody is ready to come and present. And yeah, so hopefully we get back on track with the projects, because now there are no more assignments that are due. The last one was this morning. On next Monday, I'd like to go over 3D visualizations. I wanted to do originally a lab on that, but I think it's too much. So I'll give you some examples, and we're going to look at the code, mainly try to understand how you can leverage them if you need to use those. And then I'll show a little bit of a study guide for the final exam. This actually we'll hopefully have it done this Wednesday. So we'll work more specifically on resolving technical issues for the projects, and also here on the 13th. There are 2 quizzes that are left for both of these lectures, 10 and 11. So I'll open this one later this week, and then this one also later next week. So by this Monday, 11/22, that is the week of Thanksgiving, we should be done with the quizzes. And then we have 1 lab left on the 29th. So hopefully at this point you have something that is working with in terms of the dashboard, with placeholders for the charts that you didn't have time to get in, and you have basically a little bit more than a week to finish it up. So the deadline, that is the last moment at which you can submit the project, will be on December 3rd at 5 p.m. because that's the when the classes end. So yeah, we can push it by a few hours, but hopefully we can get there. Okay, so if you have questions, again, we can discuss this in more detail on Wednesday. And now I'm going to go with the lecture. Yeah. All right, so we looked at how we understand things that are simple and that are seen very quickly. Those are the pre-attentive features. And we saw from the standpoint of using those features in visualization when it's helpful, and how you do it. We also saw a little bit how the brain forms patterns from simple objects that are detected, and today we're going to see this in a little bit more detail. And this falls under the umbrella what is called pattern recognition. As we recognize patterns, eventually we need to keep them in memory so that we can use them. And this is essential when you're looking at visualizations, because either there are animations and things change, or you're looking from one chart to another chart, and you need to relate the data. So you need to be able to keep those visual patterns in memory to understand either the data or the information that is displayed. So we're going to go through that in a little bit of detail, not too much, because obviously what is interesting to us is the design part as opposed to the perception part. but I'll try to give you some hints on how the perception works, because for one, it helps you understand a little bit how the process functions, and also it helps you put it in practice when you're creating charts, so you remember that how important these are. The other reason is that if you think in terms of machine learning, a lot of this is the inspiration for the machine learning algorithm that you're using, especially for AI. And there are some models that are working off the memory models, or at least how we understand memory, that are interesting to look at. The second part is the Gestalt. So this is a theory that was put forward by a school of psychologists in Germany in the last century. And it's still relevant because they thought about how we understand visual patterns. And those they encapsulate into some laws. We're going to look at the different laws that comprise this Gestalt theory, because they're useful from a point of view of design. It's good to have them in mind. They basically formalize what we have learned and what we're going to learn today in terms of how we process visual information. And so that's a neat way to basically keep in mind what works when you're dealing with visual information. The last part is more of a theory on some of the things that we've seen last week, in particular in the grammars. So you might remember the vocabulary from ggplot2 and Altair, where they refer to marks for the visual objects that you're using to encode the data, and the encoding is the mapping between the data and those marks, right? So the people who have worked on that in the past, and we're going to see what was done. So we clarify a little bit that part of the vocabulary. Okay, so the pattern recognition is basically about recognizing something from your visual input based on information that you have stored in your brain from a previous exposure. So the way it works is that you don't need to think about when you want to recognize some objects that are in front of you. The brain does it automatically, and that's why it's subconscious. If you use attention, then you're putting scrutiny on some particular object, and that's where you're making those movements of the eyes to look at different parts of the object. And that helps you recognize specific features that tell you more about the object. And those features you automatically compare with what you have stored in memory. And so we're going to look at both the memory models, but also at how these patterns are formed and how we perceive patterns, what type of configurations of objects will lead to a pattern. So the people have looked from a physiological point of view of how it happens in the brain, and there is a model that we're going to look at that says that this is through a certain pathway in the brain, meaning that the information goes through certain particular areas in the brain that people call the what visual pathway, and we're going to look at that. And not unlike what we've seen in terms of information processing by the visual system, it is a top-down and bottom-up processing information, because here what we're doing is obviously processing information that is related to patterns, but it is still visual information processing. So it goes both ways. It goes from what you see to what you have in memory, and from what you have in memory to what you see. And the connection between the two is also to some extent done through the visual pathways. So one evidence of the fact that is subconscious comes from this phenomena is called apophenia, where we basically, if we are exposed to random stimuli, we're going to end up to trying to make sense of the information that is there. And oftentimes we see things that are just not there. So you see typical examples here of these pictures that cast that is taken. This is on Mars. So the shading is such that we see a face there. Obviously, if you change the way the scene is shaded, you will see that there is no face at all. But it's surprisingly clear to us that there is some type of work art here that was done on Mars, and that's really just because our brain is thinking in terms of making sense of the information that is there based on what we know. So we're very good at recognizing people. So we're going obviously to see faces everywhere. So this likelihood of seeing patterns, that is called again apophenia, is increased in the case where you have previous exposures. So the face is again a good example. We've been exposed to faces since birth, and we're very good at reading them. So that's one of the main things that the brain is working on subconsciously when it looks at a scene, to try to recognize if there are faces there. And we're very good at seeing if the face is a happy face or a sad face, because in terms of evolution, we want to make sure that this is not a danger. And so we want to minimize typically the misclassification errors that can occur. And the brain is basically wired to do that. So the technical word that we use for pre-impressions is called priming. So in this image, now, can you see something in this? Can somebody see something? What do you see? It's not a trick question. Yeah, there is a dog. Everybody sees the dog? It's a Dalmatian. It's a dog with black spots. That is, his head is down, and it looks like he's drinking, and you see it from his behind. Yeah? Right. So the first time that you see this picture is going to take you a while to see the dog. If I show you the picture a second time, now or in the future, you're going to say, boom, the dog is there. Yeah? And so that's what we mean by priming increases the chances that you're going to see the stimulus. And this is working in part with the visual store that we have in our brain that takes care of storing the visual information. And we're going to see this a little bit later in terms of what particular store is involved here. So the pathways that we have in our brain that people have found out by doing research are these two. The one that goes on top of the brain there is called the where pathway, where as in location. And this is the part that is most used when you're trying to grasp an object. And you need to correlate what you're seeing with the position of your hand so that you actually grasp the object and don't close your hand on the air that is nearby. And so there is a feedback loop between the visual information, what the brain understands of the scene, and your movements. So the brain is basically driving your movements based on the visual information, right? So that's the where pathway. So this is mildly useful to us, aside from simple things such as obviously interacting with components such as buttons that you might have in the visualization. But we're making the assumptions that because this is subconscious, it's something that everybody is gifted with. So we don't really worry about that part of coordination, right? Manipulating the mouse is not a concern in terms of the visualization. What is a concern is the input, that is, are people able to understand that they need to press on this button, and do they understand what is going to happen when they do press the button, right? And that has to do with the what pathway, where we're basically understanding and processing the visual information that comes in from the eyes and understanding what is in the scene. And so this what pathway is what is most of interest to us. Now, this pathway, you can trigger it even without visual input. That seems a little bit strange, but you can close your eyes and you can materialize some scene in front of your eyes and just think based on that, right? And that you do it all the time. So if you're doing simple calculations in your head, or taking in a chart, and you can close your eyes and you can just think about it. In that case, you don't need to have. So if you're dreaming also, you can do it completely subconscious. So that's basically the mechanism that help us also think. The limitation there is obviously when we talk about visual thinking, is how much visual information you can take in and then close your eyes and think about it. And there the resources is again the memory store that we have available that we're going to look at later. And the attention, and we're going to see that those are basically linked. Yep. So you remember, I think we have mentioned a little bit the visual areas at some point. So here you have a graphic where you can see where they are located. And you see that they're not all neatly arranged. There are these areas here that are by their own. You remember that we talked about the lateral genicular nuclei that are here in the middle that take the information from the eyes, and we say that whenever you're doing saccade movements and you're moving your eyes very fast, they shut down the information because otherwise it confuses the brain. But aside from those particular areas, you see that it's mostly concentric areas between V1 to V4 that comprise the most of the visual system areas. So V1 is where all the information first lands. And so obviously there is where you're going to process the simpler type of information. And we've seen some example of that. In the form of the pre-attentive features. And that's not a coincidence because in order to do it very fast, you need to have the neurons that are as close as possible to the signal in input. You don't want to do too much processing. So here in this V1, V2 area, that's where you get most of the simple clues, such as lines, and you start looking a little bit at angles, movement of patterns, but we don't necessarily try to recognize anything, right? As you move up to V4, V5, here the information is really the patterns. And those patterns can be a phase or something complex. And there is much more processing that is needed. So we're going to look at those in turn and try to compare the information to try to understand what is it that is useful for us in terms of design. So again, V1, V2, that are referred to as the lower visual cortex, are the first areas where the information arrives. And the features that are processed there are very simple. Typically, all the features that we've seen involved in pre-attentive processing. So I give you here an example of what may happen. So you have, say, some neuron that is in V1 is getting some input, which comes from different cells. First, it's integrated into the eye by a receptive field in the eye, where you have cells in the eye that are imaging, say, as a line. Then it might get some input from another few neurons that are firing on that particular stimuli, and it does this as an integration, right? So you have really a few levels of neuron that land at this V1 neuron, and then if it's a very specific stimuli, is going to fire. So say that this one is interested in just detecting vertical lines, and that's all it's going to do. So if he sees a vertical line, it's going to light, switch on the light for that. And that's about all that is going to do. In the higher, in contrast, in the higher visual cortex, that is V4 and here MT V5. Yeah, don't worry about the either. We'll simplify it. So essentially V4, V5. The MT is the medial temporal. It's another name for V5. So you can just think here V1, V2, and here V4, V5. The V2 you see is a little bit in between, so we're not differentiating it here. So here we have really complex patterns that we're looking at. And so in this particular example, a neuron that is in these areas is going only to recognize a very specific pattern. So it's your brother or sister face or your mom's face, and it's going to fire whenever it gets that information. Yeah. So if we think in terms of information between the lower and the higher visual cortex, you see that in the lower visual cortex, we have very little information. We know that there is a vertical line, but that's about it. In the higher visual cortex, it's very detailed. We know exactly that is a particular phase, that it's a phase, it's a complex pattern. And so there is a lot of information here if you measure it. In terms of how localized the features that are seen are, in the lower visual cortex, the line is very well localized. You're going to know exactly where it is. The face we don't really care how well the eye is localized. What we care is that this is the face of X, and both his eyes are there. And either he wears glasses or not, but that's about it. Yeah. So the localization is high in the lower visual cortex, but it's not that good in the higher visual cortex. How specific we are in the lower visual cortex? We're not specific at all. So if you think in terms of the line, any vertical line will do. We don't care. The neuron that is going to fire for a vertical line, it doesn't care. As long as it sees a vertical stimuli, it's going to call it. So here, how specific it is to vertical lines is very low. Here, how specific we are to take the example of the face is fairly high, because there we're going to recognize exactly which face that is. The experience in terms of universal individual, remember that we say that universal is that you can count on it, that everybody has it, and the individual is that it's mostly learned. Now the face example here is a little bit of an odd one, because we're genetically programmed a little bit for looking at faces. So there is a part of learning, but we're also very good with that. But in general, when you look at patterns, are we going to see that are not patterns that you're wired to learn? Then the higher visual cortex requires learning to deal with those patterns. And this you can see it in common life, right? When if you're coding in Python, then there are some patterns that become just obvious with time. Just a block of code, you're going to very quickly see what it is about. The first time that you see it is going to be very difficult, right? To understand. What you're going to see is just the character. And there it's more the lower visual cortex is going to work until you can evolve memory and learn from the patterns so that you can recognize them. And that learning is fairly individual. So how this is working in practice. So this is the example with the line that I'm showing you, where the V1 neuron that we were discussing earlier is here shown in red. And here we put, for the sake of the example, some neurons that are in the LGN, those that decide if you should see things or not. And in this case, they're just passing through the information. And you see that what they're passing through is information that corresponds to a set of cones that are the cells that are in the eyes, and rods also, obviously. with a receptive field. I think we saw some example of that in the past. Basically, an area that is taking visual information, and this is integrated at the level of the V1 neuron, right? Now, the verticality of the eyes obviously has to do with how vertical is your head. So here we're supposing that we're looking straight, and so these are just in one line. And in the case we are looking at a vertical line, then all the pluses here are going to send a positive signal that the neuron V1 is getting from all of them, and it's going to say, oh yes, here I see a very large response for a vertical line. Yeah. If the line is not vertical, then you see that the overlap between the plus regions in the line here is much less. So here the V1 neuron that is going to respond to the vertical line is going to say it doesn't look like a vertical line because that's what my receptive fields are telling me. So this process of integrating information is called convergence. So you see that the information is converging toward this V1 neuron. And when we think in terms of how a given neuron is tuned to a given stimuli, this is what we refer to as neuronal tuning, meaning that this neuron is tuned to look at receptive fields that are going to be giving an important response only for vertical lines through the convergence process. So with this in mind, now we can discuss a little bit some more properties about the lower visual cortex and then the higher visual cortex from the standpoint of the design. So lower visual cortex, typically what you're doing is that you're looking at things very quickly because there is not much information, and so there is not much processing that you need to do, and you do it in the areas that are first hit by the signal. So this is very fast. Typically, it's 40 milliseconds, and therefore it's pre-attentive. So all the pre-attentive features are part of this, which you can see there. So some of them listed. So strong tuning in the sense that we just saw to anything that is orientation. So here you see these two vertical lines. This one is not vertical. With respect to this one, we see it very clearly, right? And here you see also alignment. I think we're very good at seeing these things. So strong because of the strong tuning to orientation. Spatial frequency is typically here, right? So we're able to see if you have vertical patterns or horizontal patterns. We're able to see if those patterns are regular or not, and color. So we're also good at discriminating colors, with the caveat that obviously with color you have the colors of the background that may interfere with the color of the feature that you're looking at here. That might be inside of the frame. Obviously, pre-attentive, it means that there is this notion that we have discussed of feature hierarchy. And here you see a typical examples where that is from where we see that some pattern is better at being seen than a different one. So the corners here, according to where they're more powerful, they generate more powerful responses than edges, which might be useful in terms of if you want to quickly highlight a lot of points. you can do a crosses as opposed to a dot. That might be useful for making that pattern more obvious and faster. So I put at the bottom some of the timings for the pre-attentive and non-pre-attentive tasks. So the non-pre-attentive requires the saccade movements of the eyes, which takes quite some time to start. You can see with respect to the 40 milliseconds up there, it's about 200 milliseconds. And then they last up to as long. So it's between a factor of 5 to 10 of what you are getting here. As soon as you start moving the eyes, and when you move the eyes, you're basically using attention because you're actually going to scrutinize the scene. And this is driven by the Watt pathway, right? So here is the higher visual cortex. So there what we're looking at is much longer time that with the lower visual cortex. We're more tuned to things that are global in nature, how the shape of objects, how the pattern is organized in the scene. And that can include groups of patterns, motions of patterns, including large ones. So some of the brain processing that is done in this area is trying to generalize, because we want to be able to recognize classes of objects. So one thing that Ware points to is this notion of a generalized contour, meaning that oftentimes we just need to see the contour of an object, and we can recognize that object just from the contour, right? So here, for instance, for the dog, we don't care about this is good enough. So the claim is that the brain is doing some type of representation like this. That obviously for it to work, it means that it needs to be invariant to the direction of sight towards the object. So these contours, they're not just from one point of view, but they're from all points of view, and we're usually good independently of the direction of in which we look at the object. The last one is here the tuning to motion patterns of large pattern. I have a little example here that is going to show you that. So this is just random noise, and I think I cut out the pattern upright, and I just move it, and you see as soon as it stops, you're unable to say where it is anymore. And it's exactly that. This is all done by before so here we don't do this attentively because we need time to integrate the information. So this is done by the higher visual cortex. So in terms of design, where thinks of objects as composite forms that are composed of one or multiple patterns that he calls chunks. And what he refers to an apprehendable chunk is something that you can remember. So what is the set of patterns that you can form together that you can recognize as an object, and that depends on the number of components that you attach to it. So you see that there in the examples that usually if you go, for more than 3 components, then it becomes complicated to recognize it. Recognizing meaning that if I take one of these objects and they are associated with some data, and they have multiple combinations, can you make up the association, right? So obviously, if I show you this thing and then I ask you to recognize it again, you will do it. But as you have different forms that are combined together, will you be able to do the mapping, right? And so we're going to see that this has to do with memory in a minute. Let's see. Yeah. Yeah. Just a word of vocabulary. Unturned pattern is a pattern that you haven't seen before, right? That you have not learned, but that you can apprehend. Therefore, you can learn it and learn to recognize it. And when he talks about apprehendable chunks, is interested in things that you can learn at once. So know that you're going to be exposed to it multiple times. And this is because when you think about putting some symbol for a class of your data, say, and then you're going to display the symbol into a legend, then you want that people just look at the legend once, and they then go to the graphic, and they've learned what the pattern is, and they can recognize it in the graphic. Yeah. So here the rule is that you don't want to make those patterns with too many components, because then it becomes difficult for people to remember. Yeah. A similar mechanism that requires attention, because here we're talking about complex patterns. So again, we're looking at things that are happening in the higher visual cortex, where you have time to process the information. So you're consciously learning the information. Is this idea that you can filter through different patterns and tune to one particular pattern while somehow abstracting the others. And that's called this selective attentional tuning. So you can selectively tune your attention to a given pattern. Yeah. And so this is used a lot in maps, because maps have multiple layers, and we make maps in that way because it's practical for the visual system to be able to focus on just one of the layers and get the information for that. And here you see it in these examples that are not map related, but I think they're from where, and they make well the point that you can on the left one here focus on the yellow text, and then you can read the numbers without any problem, or on the blue text, and so on, right? And the rest of the patterns are not disruptive, up to the point where again things are not too similar one to the other. So here in the case of the text, you see that the background here and the color of the text are different, but if they would be on the same color, because the symbols that are in the background are quite similar to the letters or the alphabet, then it would be disrupting the pattern, right? So this is similar to the what we saw with the pre-attentive features, where you want the pre-attentive features to be as farther away in the space of the configuration from anything else that is in the display. For the selective attentional tuning, you want the same property to be true, otherwise it's difficult for us to do it. And then you remember that we call these conjunction search, that is that where you actually need to scan the display because there is an overlap between the visual properties of either the pre-attentive feature, that the target and the disruptor, or here you could use the same vocabulary for the different layers that are involved here in this attentional tuning. Yeah, the attentional tuning is kind of looking at patterns in addition to what we've seen with the attentive features. So what happens with in addition with group of patterns is that we are, and this is probably an adaptation from the fact that we can recognize things from different points of view under different lighting. So usually we're very good at recognizing patterns, even if there are very strong disruptions. So this is my son when he was tiny. He was playing with the phone, and I think this is one of the filters. So I mean, you can recognize that this is a face, right? So even though there is a strong distortion, and this is the same thing that we're using when we do a map where we distort the areas based on values, because we can still make sense of the map of the general shape of the country. So you will see that it's Europe, even though the distortion that is encoded in the data might be very high. So we talked about the generalized contour. So this is another implication of that idea that you can simplify things, and if you do, we're still very good, if not better, at understanding the information that that is presented. So here I give you some examples. So the smiley faces, they're very popular these days as a symbol because people are good at reading faces, and you're very good at discerning between the happy and the sad face with multiple degrees in between. So the top example there is it's a medical scale for pain that you might see in hospital. So that is called the Wong Baker faces. This one has snapped it at the airport. You've probably seen those. It's a customer satisfaction display where you basically say how happy you are with the services that are provided to you. This one is a drawing by Galileo of Jupiter's moon, and so this is you see the sketches have been around for quite some time now, obviously, but you see the way this one is presented, it's really in the form of a table with both the Jupiter and the moon that are sketched out by symbols, right? And it makes a process that is fairly complicated. These moons are revolving around Jupiter. Simple to understand from a timing perspective for somebody who is observing it. So the symbols, and I think this is I'm going to probably finish on that. Are another simplification of schematic drawings that are useful to use in graphics. And also in user interfaces. So you're not without knowing that you throughout dashboards and other interfaces that we're interacting with, there is a lot of symbols that are used, and it's because they were very good at remembering the symbols, recognizing them, and they have a low attention requirement. So the anchor, you don't need to think too much to recognize that. And if you learn that this is used in a certain context, say in a word processor, to set up where the text start is, or we saw it in the anchor for the text, we did it in HTML and or in Inkscape. Then you remember that association very easily, and you just need to see the anchor in the user interface to know what its use is. So people have developed all sorts of icon libraries for that that are useful, and they're also useful in the sense that they make the association by doing basically what are called visual or spatial metaphors. So the battery is a good example, but here the star is also a good example of that. Now, how do you, here it's a little bit more elaborated. We're looking at the grouping of symbols. Here, because there is an outline, then we understand that all of these are part of the same entity. The color might be able to tell you that, and so on, right? So here we see that we have 4 dots and here 3 dots. So this is one unit. We should see it as a unit. So all these rules we're going to see a little bit with the Gestalt theory that basically formalizes those ideas into simple rules that you can use to displaying information. So these icons are they didn't appear just with the web. They were there a long time prior to that. And if we can find the one source of it is probably Otto and Marie Neurath in 1935 that started creating this idea of symbols that everybody can understand. So here you see a simple application where of the symbol is that is still used today for street signs, and they call this isotype for International System of Typographic Picture Education. Okay, so it's basically can I make simple sketches that people can very quickly understand and use. So obviously with driving you can't use much attention, so you need to understand them very quickly. And this is the source of the icon libraries that we're using today, right? That's still the basic idea behind it. So this is a chart that Otto Neurath is attributed to, that is fairly famous from the 1800s. And here what is showing is basically a stacked / staggered bar chart, right? Because we have bars here and we have bars here that are all built with symbols. Is using this box to associate on top of the color. So it probably would work already with the color, but then the fact that it's adding the smokestack here makes it a sort of a legend, so you understand that all these are units of factory, right? And you understand it right away. Then if you want to know what the black little men there are, you need to go and read the legend. So basically, the chart is comparing the production of linen, I think, that is here materialized by the rolls for different years with how many workers are working as part of a factory and how many are weavers. And you see that the production, whenever you get to the factory, is 10 times what you had the 60 years prior, where there were almost no factories. So all this is done with what Otto Neurath calls isotypes, that today we call icons or symbols. You pick the one that you like. So I'll finish with, and then we'll do a quick break with some things on the visual memory. So up until now, we looked at patterns, but we didn't talk much about memory. So the model that is understood today is represented here in terms of these three types of memory: the iconic memory, the visual short-term or VSTM memory, and the long-term memory or VLTM. So let's look a little bit of what properties they have, and we can contrast this, and then we can also relate it to some of the things that we've seen. So the iconic memory, unlimited capacity, obviously is limited by the amount of information that you're getting through your eyes, but this memory can just take it all. So whatever is coming from your eyes, you can get it in. And so it's unlimited. But it's fairly short. It's less than a second that you can keep it in memory. So it's high bandwidth. That works unconsciously, meaning that you don't need to think about it. And what it does is that it provides temporal integration. What that means is that as you move your eyes around, you remember that the saccades are very fast. So the LGN is shutting down things in between. And this memory is giving you continuity between a snapshot here and the next snapshot that is not exactly at this, at the delta of time between the previous and the next, knowing that there is an interruption in between. So, and the interruption is due to the saccades because, again, we move our eyes so fast that it wouldn't make sense for the brain to process the information. So at some point, the brain is just getting no information, and then it gets a new set of a new image, and it uses the iconic memory to ensure continuity between objects seen in the first image and objects seen in the second image in between the interruption. So do you remember the two types of blindness that we've seen? So there was the inattentional blindness, and then there was the change blindness. So which one here would relate to the iconic memory? So the attention blindness was the gorilla video, and the change blindness was the car video where the street was changing, right? And you remember that in the street, there were these interruptions. So the interruptions is typically what happens with the saccades. So there, what we were doing with the longer interruption is basically messing around with the iconic memory. Yeah. So visual short-term memory. So this one is the inattentional blindness, because there we go to 30 seconds. So you have the time to process the information, to use attention. So this is the information that you use when you look at the store that you use, when you look at the legend of the graphic, and you memorize the keys. And then you look at the graphic and you make sense of the data knowing the mapping, right? Visual short-term memory. The visual long-term memory is not that relevant to us because this is really the long-term memory that you have, but that is not really relevant to what to our topic, that is the information visualization. Yeah, so these are things that you will remember for years, right? So less important. I mean, it might be important at the level of information. If you ask what users have in terms of background, if you're doing an infographic, but for interpreting the information in visual displays from charts, then it's not that relevant. So why? So you remember probably this graphic from my candles that I showed you that was showing that we have gigabit force of information, that is visual information is coming in from the eyes. But then as soon as we need to really think about what is available to us when we use attention, there is very little information. So here is basically the explanation, and the explanation is that as you move up from the information that is your eyes here, that is from the real world. So here we're at the gigabyte per second in terms of retinal image information. So there is a little bit that gets lost because we're moving our eyes and so on. And because yeah, just the visual processing is part of the eye. But then as soon as we move from this nerve connections to the brain, there needs to be this back and forth where we're using attention. And in order to make sense of what we're seeing, we need to remember what we just saw and contrast it with what we're seeing now. So there, the memory that is used basically to understand the scene is what enables attention, right? So if we can't remember between the saccade movements, the objects, then and if we can't remember the keys that are in the legend, when we look at the legend and then go look at the graphic, then we're really not able to understand the information in the graphic. So for that, we need to use the VSTM capacity to store temporarily up to 30 seconds the information, and that storage has a finite capacity, right? And that's create what here is called the attentional bottleneck, because you cannot put much more information into that memory store to utilize. And so you see that here we're losing towards of pointers. So eventually, if you want to store it for long term, then you lose another 3 to 4 orders of magnitude in terms of the number of bits per second that you're actually able to store. But for us, what is important is really the size of the VSTF. That when you use attention, that you don't have a choice, right? You need to use that memory store that will basically limit what you can, the amount of information that you can play with. And so the big consequence of that is known as at least it's one of the laws that people have come up with as the Miller's law. That says that the magical number is 7 plus or minus 2, which means that if you look at different objects that you need to remember, different colors, different shapes, if you go more than 7 to 9, it's not probably going to work. Now, this is a rosy picture because this is assuming that you're doing simple, here one-dimensional judgmental task. So this is really how long is the segment. If you start thinking about characters, then different characters, you can recognize items if you are between 4 and 5 items at the time, and otherwise that will not work. So again, this is the size of the VSTM, okay? That enforces this. When we use attention, so if we have more than 4 or 5 keys in a legend that are of type characters, we're not going to be able to remember which one is which one. And then 3 or 4 items if you do basic visual features, that is dots, lines, corners, and there is an interference task. Meaning that while you're looking at the legend, I'm showing you something else on the side. So you need to multitask. And then you see that it's even less than before. That this is an example of what not to do for a number of reasons. But let's do a break. And then maybe we can discuss it. Yep. Okay, thank you. Right. So here it's really complicated to use, right? So how do we fix it? So to fix a chart, you need to think about what is the information that is in there. So here we're trying to compare these parties, right? And what is interesting is to know which one has the most seats, which one has the less seats here in the European Parliament. And maybe to know if they're from which spectrum of the political tendency. And so to compare this, if you ask me to do this, I would do a bar chart to start with, right? And I would do it ordered, so that you make it easy, because here you have too many keys, and so with a pie chart, I need to go with the legend and then look at the chart and then remember what is here. So it's complicated. If you have a bar chart, the keys are right under the bar, so there is no confusion there. You can immediately find the information, right? So the mapping is, so it's easier to read the data in the chart. Now, if you still want to do a pie chart, at least you should order it, right? Because here it's not order, and so it's very complicated to understand what is going on. And then we would remove the 3D, because the 3D makes it harder to understand how big are the areas, right? So if you order it, at least you know that you can rely on the order, but you may still want to know in proportion how big the blue is with respect to the red, right? And so in order to do that with the pie chart, you can order it, but I would remove the 3D that is just adding more complexity, because we need to think more about it, right? And again, we're bad with comparing areas. We're good. We're with comparing lengths, such as in bar chart, but with areas we're pretty bad. So if you can avoid it, you should. Okay, the Gestalt. So these are our principles that are coming from a school in Germany that are principles of psychology that have been applied in a school of art. So this is the symbol. And what Gestalt means in German is shape. So they were trying to understand how we perceive shapes. And by association, obviously, they went down the rabbit hole and they looked at colors and movement and so on. And they put together some rules that on how we perceive patterns. So the basic of the theory is that we perceive a set of patterns as more than the sum of its parts. So this is just some squares, some lines, and a circle. Because the circle is there, we associate all these lines and these squares together, and we see this as a face. Yeah. So the logo of the school symbolizes this idea that it's more than just the individual pieces that we understand. We see it as a totality. So they have these 4 principles, and then it's laws of how things are grouped that we're going to look at. So the emergence is that we perceive images as a whole. We've seen already this example. The reification is that we perceive more than what is there. And in particular here, you see in this example that there is no ball, but everybody sees a ball because same region actually that the following one, that is the multi-stability, that some stimuli are perceived as changing between two or more interpretations. So these two, actually also the last one, the invariance, we see things and we understand them independent of the orientation. These three have to do with what we have discussed in terms of 3D, right? We perceive information in 3 dimensions, and therefore these cones here, they're not just floating in here, they must be supported by some object, so we see the sphere that is there. This one, these lines, we see them as a volume, but because it's a transparent volume, we're not used to that. We don't know exactly which face is the front-facing face, and so we see some unstable figure. And the invariance there, I think, is obvious. And here you see that we also have this distortion that we have mentioned earlier. So all this work was done obviously before there was evidence from the science of how we understand, how we perceive objects. These are a few of the laws, and there are some more screens for laws of grouping. So the pittiness has to do with the fact that we're trying to simplify things. So instead of seeing jumbled up shapes here, we see them as individual pieces that are put together. And that's what is symbolized here by the color. So here it's obvious, but here it's also more or less the same. We see that it's a rectangle, a circle, and a square. And a triangle, sorry. Figure and ground. This has to do with the fact that we tend to separate the foreground from the background. And this shape is actually a bistable one. If you look at it carefully, here a nose. So this is an old woman with the mouse here. Or you can see here the profile of a younger woman here with the line of the tooth and the ear. And we see those shapes because we separate them from the background here, that is materialized by the line around. Parallelism, parallel elements are seen as grouped together. That's a little bit of a grouping law. See this again. So these three lines here seem to relate to the same object, even though there is no object there, but that's how we perceive it. Symmetry, we usually we like things that are symmetric, and we usually think that there is some center that needs to be there. So here is a simple example. Focal point, so this is not unlike the pre-attentive features. As long as the target is a point that is different in some channel from everything else around, then we see it as emphasized. And here we see that it captures your attention, but that's basically the pre-attentive features that are captured in that way. And then the past experience has to do with the fact that we use what we have in memory to understand objects. So this is looking like a traffic light, because we see those colors in a traffic light, and we don't see it as a box with a black square rectangle with 3 dots of different colors. So laws of grouping, you have them here. I mean, I can go quickly through it, but they're mostly obvious. But they're useful when you think in terms of connecting elements in the display. So if you put things together, they're seen as part of the same entity. So these dots here, and these dots and these dots, they're seen as presets. So a lot of this you use in displays when you set some text aside and with graphics, so you can use it also in terms of composition. Things that are looking the same, we associate them as being part of the same thing, right? So that's the similarity. And that you can use for using the same encodings between different charts. So people don't even need to think if they look the same, it means that you're giving me the same IQ, that is the same type of information that you're providing. The closure is that you basically complete things that are not completely full objects. So here in the case of these contours. So parts of an object tend to be grouped together and we perceive the whole thing. Like here we really see a rectangle and a circle. So it's fine to have things that are overlapping. And this we use all the time when we need to deal with overplotting. But obviously, if you have too much of that, then you need a different strategy. So that means also that some ways you can sometimes you may need to have some axis that is on top of the data, and that's fine. You can slice things. They're going to not going to create a problem. Continuity, we perceive pieces to form a continuation as part of the object. So here you see that even though the red dots and the black dots are colored based on where they one with respect to the other, so the black dots are at the bottom, the red are at the top. We still see one straight line here and one line that cuts across there, and that's because we look at the object as continuity, right? Here the common fate law basically says that things that are moving together must be part of the same object, which makes sense, right? This is often used in diagram, right? When you connect objects, entities, so objects that are connected are perceived as a group. So we do this all the time. The common region states that objects enclosed by a boundary are perceived as a group. So this we use all the time when we do dialogues in the UI, for instance, and you want to say that this block of information here has to do with the same thing. So you just put an outline around it, and that does it. Here in the picture, you will notice that we put different actually laws of grouping, because here we have the color that is shared. So these they look alike, so they look like one entity, and here another entity, and there is proximity because the black dots are close to each other, right? So they look like grouped together. So these laws you can mix and match. And this is just an example of the mix and match, or just a simple grouping laws for you to wrap your head around. Okay, marks and encodings, and there are just a few slides here, and we'll be done for today. So when we talk about symbols that we're using in visualizations, people early on started thinking about those as signs, and the transfer of information as language that is done using those signs. So the science that is behind the communicating information with science is called the semiology. And Jacques Bertin is a cartographer from the 60s that had this idea that that you can transfer information, think of visualization as systems that are just doing that, transferring information with signs, where the data is encoded by some pattern. And so the designer, you remember this picture that we've seen in the first class, encodes the information with a sign, and the user needs to decode the sign to understand the information. So with that premise, what they did is that they worked out a little bit what to use and when. So the what is basically the marks. So what symbols are you using for encoding the variables, and those they're called marks usually, or visual variables. And then the encoding between the data and the marks is called aesthetic encodings if you're in ggplot2, or just encodings or channels if you're using the vocabulary that Altair is using. So he was particularly interested in this because being a cartographer, he dealt with maps. And so the question was, what should I do in the map? Which symbol should I use for which property in the map? Because in the 60s, I mean, today the maps are very formalized. So it's obvious that here we need to use an area, and here we need to use a line, right? For the road network, now it's customary that you use a path with color encoding traffic, for instance. But at the time, how you would do these things were not clear, right? And so he thought about what were the pros and the cons of using points versus areas, which one is the more precise, and so on, right? And also depending on the type of information, if it's ordinal, if it's continuous information, and so on. Now we don't need to learn this by heart, because I think now we have enough practice that we know what works. But we're also seeing in class that the color, if you want to do encode data precisely with color, is not going to be a good way of doing it. It's better if you use lens size or position for doing that, if precision is what you want to do. People later on continued to work on this. So you see here in the late 80s to try to understand what marks are more or less precise. And here we have this is taken from the paper from McKinley in 1986. And this is not surprising. Now we're new with that. We know that these things are pre-attentive, and the differences of length and position, angle, and slope are very well seen by V1, right? As soon as we start looking at area or complex objects, so this is not V1 V2 anymore, so it's the higher visual cortex, and here things are less precise in terms of information, right? So same McKinley paper tries to contrast this a little bit more in terms of the type of data. So you can do this work. It's useful in terms of theorizing, but obviously you won't be able to learn and memorize all these connections. So what we're doing these days is that little by little, I think the visualization are becoming more and more attuned to what works, and we're so you've seen in the last homework, for instance, that all this charting for statistical graphics that are available, they have defaults that seem to make sense. And the reason is that people that have basically thought about these depending on the type of data, and they've created visual encodings and marks that are easily understood. Right, so most of the time you don't need to think too hard about these days, but you need to think when it comes to if the chart is still appropriate to the information that you want to display and to your data, because we've seen that it might not be appropriate to the data if you have too much overplotting, right? Or the form is not conducive. For instance, you don't want to use an aggregation such as a box plot if you have a multimodal distribution. And I think this is the last chart. Yeah, so we're right on time. So I'll put up a quiz on this later this week. So yeah, don't worry too much. This is just that you know this body of work. I'm not asking that you memorize this. Yeah, because this is very. I mean, some of it makes sense to me, but I was looking at the. Yeah, cool. Yeah, I mean, the color. I think that they're meaningful, but I mean, it's hard to make those lines stand if you actually use real data, right? Because if you use canonical data, I can buy it, but if you have real data, then yeah, you have all sort of problems that crop up that make disordering a little bit fuzzy. All right, so just a last word for Wednesday. We chatted a bit. For those that are online, I think I'll post them. But the idea is that we do something that is informal. You don't want to spend too much time on this, but we want to make sure that if you need help for the projects, we know where it's needed and how we can attend to that. So think in terms of how you're going about developing the charts, integrating the charts, if you have done the design, if you know which framework you're going to use, if you have a plan for making the framework work for the charts that you have, if you have done the data wrangling part that is needed. Yeah, so all those moving pieces, so that we can address them now, and hopefully in a week, 10 days, by Wednesday in a week from 10 days from now, we can maybe go back and look at whatever you have. Now, if you have done already things that are ready to, I mean, it doesn't need to be ready to show, but if you have questions on things that you have done for design, for instance, you've designed the dashboard and you still have questions about it, either about the layout or about the interaction between the charts, bring them on so that we can try to address them. And if we do it in a group setting, I think it's good for everybody. Yeah, and if you have technical questions, then we can either try to address it with another group or do it with the office hours, because now that there is really no need for the office hours aside from helping for the project. All right, thank you.